Now coming to the problem. So here you are going to analyze a two-span continuous beam. So here you can see it is a two-span continuous beam AB, ABC. And then you are having a loading of 20 kilonewton at AB span, whereas 30 kilonewton meter in BC span. So here AB span you are having a 4 meters of 2I moment of inertia, and whereas for BC span you are having a 3 meters with I moment of inertia. So that means moment of inertia is varying from AB span to BC span. And then coming to the next step, here you are going to determine the degree of freedom. So here you can see that at A support, it is a hinge support. And here B also, it is a here, roller support. And at C, it is a fixed support. Therefore, at A support, you are having a rotation, but you don't have any translation. And similarly, at B support also, you are having a rotation, but you don't have any translation. Whereas at the C support, as it is a fixed support, there will be no rotation and there will be no translation. Therefore, here the degree of freedom will be 2. So that means theta A and theta B will be your degree of freedom. So that one you are going to find out in this problem. Now coming to your next step. So here you are going to calculate the fixed end moments. So this is a beam you're going to consider now. So for this beam, what we are going to do is we are going to find out the fixed end moments. So first I'm going to draw the beams individually. Okay. So for this, as external load is acting, so to this external load, so what are the moments that are going to develop? So this is a 30 kilonewton meter. So for AB span, okay, due to this point load, so here you are having an hogging moment. Okay. So this hogging moment are WL by 8 and this is also WL by 8. Okay, as it is a symmetric loading. If it is unsymmetric, the formula is going to change. So here in this method, you are going to take the sign convention. So the sign convention will be clockwise moments, you are going to take it as positive, whereas anti-clockwise moments, you are going to take it as negative. Okay. So here for AB span, as it is a anti-clockwise moment, so you can write fixed end moment MFAB will be equal to minus WL by 8. So that means minus 20 into 4 by 8. So that means MFAB moment will be equal to minus 10 kilonewton meter. Similarly, MFBA will be equal to plus WL by 8. So as it is in the clockwise direction, so that is plus 20 into 4 by 8. So therefore, MFBA will be equal to plus 10 kilonewton meter. Similar way, when we consider a BC span, so for BC span, when we are having a moment at this point, which is of 30 kilonewton meter, so here you are going to develop again the end moments to be, as it is a symmetric portion, 1.5 meter and 1.5 meter. So here it will be equal to M by 4 moment and M by 4 moment. So that means MF BC will be equal to minus M by 4 since it is in anti-clockwise direction. So that means minus 30 by 4. So that means MFBC will be equal to minus 7.5 kilonewton meter. Similarly, MFCB will be equal to plus M by 4. So that means plus 30 by 4. So that is MFCB will be equal to plus 7.5 kilonewton meter. So these are the fixed end moments that we have been found out for the external load that is acting on the ABC beam, okay, individually. And I'll just write down when you are having an eccentric moment, okay, so that means at A distance and B distance. So what are the moments that are going to develop at these each ends? So those moments will be equal to, so total span will be equal to L. So here the moment formula will be m naught m into mb by L into 2 minus 3b by L. And here this moment will be equal to ma by L into 2 minus 3a by L. Okay. So this one A and this one B, if you just consider, I'll just write down MFAB will be equal to MB by L into 2 minus 3B by L. Whereas MFBA will be equal to MA by L into 2 minus 3A by L. So this is a negative value and this is a positive value. Why? Because this is anti-clockwise moment MFAB and this is a clockwise moment. So this you can use when you are having a eccentric moment. So here we are having a symmetric moment. So therefore it is m by 4 and m by 4. Okay. Next, by using a slope deflection equation. So these are the generalized slope deflection equations. MAB will be equal to fixed end moment plus 2ei by L into 2 theta A plus theta B. So that is moment due to the rotation. And next is minus 6a delta by L square. Here 2ei by L has taken common. Therefore 3 delta by L. So this is a moment due to the settlement. Okay. And similarly, MBA is also equal to MFBA plus 2ei by L into 2 theta B plus theta A minus 3 delta by L. So here in the above problem, we are not having any settlement. Therefore, delta will be considered as a 0. So these two terms are going to be there, not there. Therefore, now the slope deflection is going to become MAB and MBA. So you are just having the fixed end moments and the moment due to the rotation only you are having, but there is no moment due to the settlement. Next, we are going to substitute the values here. So that is MAB will be equal to, so MFAB you got it as minus 10 kilonewton meter, and whereas I is 2I for the AB span and the span is 4 meters and 2 theta A plus theta B. And by simplifying the above one, you're going to get this equation. And similarly, when we do it for the MBA, so that is fixed end moment plus rotation moment. So by substituting MFBA will be equal to plus 10 kilonewton meter. Similarly, I is 2I and L is 4 meters. Therefore, by simplifying the above, you're going to get this equation for MBA. And then similarly, when we do it for the span BC, so MBC will be equal to MFBC plus 2ei by L into 2 theta B plus theta C. Here in the above problem, theta C is a fixed support, therefore theta C will be equal to 0. So by simplifying the equation, you are going to get this. And similarly for MCB also, by simplifying this, you are going to get this. So here what we have done is theta C we substituted here as 0. So this is the MBC equation and this is the MCB equation. So this is simplifying, you're going to get minus 7.5 plus 4ei into theta B by 3. So by simplifying this, you're going to get 7.5 plus 2ei by 3 into theta B. So this is your MCB equation. And then by use step 4, you are going to use the equilibrium equations. So coming to your equilibrium equations, I'll just draw the figure. So here the supports are A, B and C. So here MAB moment is obviously 0 since the support is hinge support. And here this is a joint equilibrium condition, that is sigma MB will be equal to 0. So that means MBA plus MBC will be equal to 0. So this is the next support. Okay. So here by using this MAB equal to 0, you are using the equation, and this is an equation 1 by simplifying. And similarly, MB moment at this joint will be equal to 0 summation. So that means MBA plus MBC will be equal to 0. Therefore, this is 10 plus EI into theta A plus 2 theta B into EI minus 7.5 plus 4 EI theta B by 3 will be equal to 0. So by simplifying the above equation, you are going to get this second equation. And by solving these 1 and 2 equations, you are going to get theta A to be positive and theta B to be negative. So that means your theta A will be your clockwise rotation and theta B will be equal to your anti-clockwise rotation. So this is again a sign convention in a slope deflection equation. Now coming to your next one, drawing an elastic curve. So coming to drawing an elastic curve. So here we already got theta A as positive, theta B as negative. Now drawing the elastic curve. Okay, so these are the supports A and this is a support of B and this is a C. So this is A, B and C. So for here to draw elastic curve, so just once again. So here you are having a rotation at A. At B also you are having a rotation, but coming to C you don't have a rotation. So here this is the elastic curve. So when we draw a tangent to this point, so when we draw a tangent to this point, so this is in the clockwise direction. So here theta A will be equal to 6.325 by EI. Whereas at B, when we draw a tangent, so it is in the anti-clockwise rotation of theta B will be equal to 2.65 by EI. Whereas here theta C will be equal to 0. So this is an elastic curve. This is positive, so clockwise. So this is at B, it is negative. Therefore, it is anti-clockwise direction. So this is how you're going to draw an elastic curve for this problem. Next, after getting your theta A and theta B, so you're going to substitute in the above equations. And then finally, you're going to get MAB moment to be 0, MBA moment to be 11.03, MBC moment to be minus 11.03, MCB moment to be plus 5.73 kilonewton meter. So these are your final end moments. So how to draw a Benny moment diagram? So these are the final end moments just I have drawn here. And then you're going to, so we are going to draw a Benny moment diagram for this. So just we will draw the actual diagram. So this is, okay, so this is A support and this is B support and this is C support. And here you are having an external load of 20 kilonewton. And here you are having a moment of 30 kilonewton meter. And this is 2 meters, 2 meters, 4 meters of 2I moment of inertia. And this is 1.5 meter and 1.5 meter. And this is 3 meters of I moment of inertia. Now coming to the Benny moment diagram, we will just see here. This Benny moment diagram will be equal to free moment and fixed moment. So how you go, first we'll draw the free body diagram now. So for this beam, so sorry, this is A, B and C. So this is also A, B and C. So AB moment, we got it as 0. BA moment positive clockwise, BC moment negative anti-clockwise. So which is of 11.03 kilonewton meter. And this CB moment to be again positive, which is of clockwise, that is 5.73 kilonewton meter. So now for this, what will be your bending moment diagram? So this is a final end moments. So for this, you are going to have the this diagram to be a fixed bending moment diagram, plus whatever your simple bending moment diagram. Simple bending moment diagram will be equal to, so this is 20 kilonewton. Okay. So here we are writing only a simple support. So here we are going to have a reactions, that's all. And similarly here also we are having an external load of 30 kilonewton meter. So which is of 1.5 meter and 1.5 meter. So as you are having an external moment of 30 kilonewton here, so here you are going to have a reactions of upward of 30 by 3. Okay, so that is of 10 kilonewton. And since it is an upward, okay, so here it will be a downward of 10 kilonewton, right? So for this, by superimposing these two, that is fixed end moments and simple and free bending moment, you're going to merge these two things. You're going to get your final bending moment diagram. So I'm going to draw first the free bending moment diagram, that is due to the simply supported. So here you are having 20 kilonewton. So it is a W L by 4. So that will be equal to 20 into 4 by 4. So that is 20 kilonewton meter. So which is of positive sign, right? Similar way, just extending here. So this is A, this is B, and this is C. So now you're having 10 into 1.5, which is hogging in nature. So here the sign convention for the bending moment is, so this is sagging moment, which is of positive value. So when we cut a section at this center towards, so this is your left side, this is right side. So here when the arrows are upward, you're having a sagging moment. When the two arrows are downwards at a section, you are going to have a negative moment of hogging moment. So this is a sign convention. So coming to this sign convention for a bending moment diagram. So here you are having a hogging moment of 10 into 1.5. So that means here you are having a 15 kilonewton meter. Okay. 10 into 1.5, 15. So here also you're having a 10 into 1.5, that is 15. Again, this portion, it will be a 0. So this is a positive value of 15 kilonewton meter, and this is a negative value of 15 kilonewton meter. So this is a simple bending moment diagram for the external loading condition. Now coming to the fixed bending moment diagram. So you can see here at A you are having a 0. At B again you are having a hogging moment of 11.03. So that means here you are having 11.03 kilonewton meter here at this point. Again at this point you are having a 5.73 kilonewton meter. So that means some value here. So we can just draw. So this is a negative moment, and again here this is also negative moment. Okay. So now what is our final bending moment diagram is, the shaded portion will be your final bending moment diagram. So at any point, if you want to know the bending moment, so you can just cut this section, and the magnitude of these two, you're going to get your bending moment value. So for suppose if you want at this loading condition, so the bending moment value will be equal to the total ordinate of this, that is 20. So 20 minus this ordinate is going to give the shaded portion value. So that will be your net bending moment. So this is your final bending moment diagram. I hope you are able to understand this. Next, coming to your shear force diagram. So shear force diagram, for drawing a shear force diagram, you are going to find the reactions first. So first we'll draw the figure. So this is a fixed support. So this is A, B and C. And this is a loading of 20 kilonewton. and this is 2 meters, 2 meters, and which is of 4 meters. And again, it is a 30 kilonewton meter, and which is of 1.5 meter and 1.5 meter. So which is of 3 meters. Moment of inertia is I, moment of inertia is 2I. So after getting this, we are going to draw the free body diagram again. So this is a free body diagram. So MAB moment is 0, and MBA and MBC moments are 11.03 kilonewton meter, whereas MCB moment is 5.73 kilonewton meter. So this is C. So now you're going to place your external loading, and then you're going to find out the reactions to draw the shear force diagram. So here the reactions are RA. For this, it is RB1. And again, this is RB2. And here it is RC. So coming to this portion. So here you can say moment about A will be equal to 0 since it is a hinge support. Okay. So now we are going to write moment about this point. So that means RB1 into 4 minus 11.03 minus 20 into 2 will be equal to 0. Therefore, RB1 will be equal to 12.75 kilonewton. Whereas RA plus RB1 will be equal to total the external load, that is 20 kilonewton. Therefore, RA will be equal to 7.25 kilonewton. So this is your RA and this is your RB1. Similar way, when I take in this BC span, moment about B will be equal to hogging moment. So that is minus 11.03 kilonewton meter. Therefore, RC about this point, about B point I'm considering, RC into 3 minus 5.73 minus 30 will be equal to minus 11.03 kilonewton meter. So here RC will be equal to 8.23 kilonewton, whereas RA plus RC will be equal to 0 since there is no external loading. So this implies RA will be equal to minus 8.23 kilonewton, which is of upward reaction, or 8.23 kilonewton, which is of downward reaction. So this is about RA and RC. Now to draw the shear force diagram, the sign convention for the shear force is, so when we take an element, so towards your element, the left side is upward and right side is downward. So that means they're having a clockwise shear. So clockwise shear means positive shear force. Similar way, when we are having towards your left side, it is a downward reaction, and towards your right side, it is an upward reaction. So which is of anti-clockwise direction. So that means the sign convention will be negative. So by considering here, so RA is upward only, RB1 is upward only. So which is of simply supported. So here, as it is a simply supported, you can just draw. So this RA is 7.25 kilonewton, and whereas your RB1 is 12.75 kilonewton. So till this B point, again at B point, you're having a downward reaction of 8.23 kilonewton, and this is upward reaction of 8.23 kilonewton. Okay, so reactions I'm just rounding off. RB1 is 12.75 kilonewton and RA is 7.25 kilonewton, right? So now it is in anti-clockwise ratio. So therefore it is of negative value only. Okay, so this this value will be 8.23 kilonewton and this point will be 8.23 kilonewton. So which is of negative and this is of positive. So this is A and at this point it is B and this is C. So this is a final shear force diagram we are going to get. So you're going to shade this portion. So this is final shear force diagram, SFD. Okay. I think this is clear. That's all. These are the references that have been taken. Thank you.